Hi everyone, my name is Jin Yao, along with Daniel. Today, we'd like to take you along with the journey of migrating Pinterest Spark cluster. A brief introduction about ourselves. My name is Jin Yao. I'm a tech lead at Pinterest for Ads team. And previously, I had spent many great years at Facebook and Hulu. A lot of my work was focused on building large-scale distributed computing systems.
And this is Daniel Dai. I'm a tech leader at Pinterest data team. I am a PMC member for Apache Hive and Pig. And before that, I was working in Cloudera and Hortonworks and Yahoo.
Today in this talk, we will cover following topics. First, we will share the high-level overviews of our big data platform, then the performance of Spark join in this platform. Next is the S3 eventually consistent model we have been dealing with. Then we will talk about difference between primary storage, HDFS and S3, then scheduling system, Mesos, and Yarn. We will conclude our talk with how Spark has been used in Pinterest. First, let's take a high-level overview of our big data platform in Pinterest. From search to ads, machine learning to recommendations, nearly every team within Pinterest relies on the big data platform in some way or another. The big data platform team is responsible for providing a stable, reliable, and efficient ecosystems for engineers and analysts to manage their and transform their data. Pinterest has been building our own in-house big data platform, leveraging open source projects. Projects we use are HDFS for storage, Mesos and Aurora for resource management, and scheduling, Spark, Hive, and Presto for data processing, Kafka for logging. The big data platform at Pinterest is constantly evolving in order to fulfill the ever-changing needs of our users and to stay up to date with the latest cutting-edge technologies. Over the last year, our team has been working on migrating to our next generation big data platform. As shown in this chart, from the high level, the most significant changes are changing our resource management and scheduling system from Mesos to Yarn, and switching our primary storage from HDFS to S3. Now the migration has finished with great improvements in many fronts, from performance to efficiency, from debuggability to cost savings. We will share our wins and learns in this talk. As any big data platform, performance always plays one of the most important roles. We have been striving to provide a platform that could run jobs performantly and efficiently. As we were building our next generation big data platform, improving performance and efficiency is one of the most important goals. We can't improve anything if we don't know what's the bottleneck of our cluster. So the first thing we did was to identify performance bottleneck of our old cluster. We took a data-driven process to find the bottleneck of our cluster by looking through all the dashboards metrics we had both internally and externally. We had identified the system-wide performance bottleneck for our cluster is local disk I/O. As shown in this chart, not having enough local disk I/O often slows down Spark jobs due to slow shuffle, which in turn makes the job and the whole workflow slow, which in turn makes the I/O resource even more scarce. And as you can see, this is a performance downward spiral that no one wants to see in their system. To understand the problem more, we need to first understand why local I/O is important for Spark performance. So local disks are typically used by several different ways. Spark writes shuffle data to local disk, and then Spark will also read local disk to serve shuffle data for reducers. Spark also spills data to local disk when memory is not big enough for some operations like sorting. Let's take a look at this problem through a simple example. This is a simple aggregation query. Essentially, what it does is to query the table to get distinct IDs and the max value of each ID. The query execution will have mapper phase, shuffle phase, and a reducer phase. Let's say we have 19 mappers and 19 reducers. Each mapper reads one chunk of input, processes, and stores the shuffle data into local disk. Then it's the shuffle phase. The goal of shuffle is to move the same ID to the same reducer. So each reducer could compute the max value of each ID. In order to do so, each reducer will talk to all the 9K mappers and ask for the IDs this reducer is responsible for. So in total, all 9K reducer talks to all 9K mappers. There will be 81 million connections. One machine can run multiple mappers at the same time. So if we zoom in and only focus on one machine, in this case, this machine has 30 mappers. All those 30 mappers share the same local disk of the machine. One mapper writes the shuffle data once, then read it 9K times for 9K reducers. So in total, 30 mappers need 270K I/O operations. Usually those operations happen around the same time because each mapper processes roughly the same amount of data and finish them around the same time. That's too many operations for our machine in too short time frame. So how did we optimize this job in our own cluster? We had done a lot to optimize our jobs. One of the most helpful optimization we did was to tune the number of mappers and reducers in order to combine small data operations into big ones. Here is as an example, we reduced the number of both mappers and reducers from 9K to 3K. Again, if we zoom in and only focus on one machine, in this case, this one machine has only 10 mappers. All those 10 mappers share the same local disk of this machine. One mapper writes the shuffle data once and read it 3K times for 3K reducers. So in total, Spark will do 30K local disk operations, which is 9 times better than before. And one thing to notice here is that reducing number of mappers and reducers also reduces the parallelism of the job. If that is too low, job won't be able to fully utilize all the assigned resources, which could regress the performance. Last year, we spent a whole month to optimize one of our most critical jobs. The optimization result was awesome with 4 times improvement, but it required a tremendous amount of manual tuning. Those tuning usually don't scale very well with data volume increase, and they couldn't be easily applied to other jobs. So not having enough local disk I/O had made Spark jobs really hard to optimize, and having system-wide performance bottleneck really put a heavy toll on every job running in its cluster. New cluster. So when we were building our new cluster, we were determined to remove the cluster-wise performance bottleneck so that each team could focus more on building impact products instead of dealing with performance issues. With the performance bottleneck in mind, we did multiple rounds of testing, trying to find the best hardware configurations for our Spark workload. Eventually, we had settled on EC2 type R5D. It's local disk optimized, which brought the local disk I/O per second from 3K to a whopping 40K. Our jobs really loved the new cluster, especially the new EC2 instance time. Jobs have seen 25% runtime improvement on average. That's without any extra resource or tuning. One shuffle-heavy job even got 35% improvement from 90 minutes down to 57 minutes. Out of all the cluster-wise improvements we have done, optimizing local disk I/O was definitely the biggest contributor. If there's only one thing that I hope you could remember after this talk, that is measure before optimize, as I always saying that premature optimization is the root of all evil. In our case, we did investigations and tests with our own workload in our cluster. So we didn't guess the bottleneck, but instead, numbers told us that local disk I/O is the bottleneck of our cluster. So switching to local disk optimized instance type is the perfect change for our workloads. Do the test with your own workload in your own cluster, identify bottleneck of your cluster, and try to optimize that. In terms of optimizations, there are 3 levels you can do: cluster level, Spark level, and job level. So you can optimize Spark at a cluster level to benefit all the workloads running in this cluster. Our example is improving local disk I/O has given us 25% performance boost on average for all the jobs without any extra resource or tuning. Next is the Spark level. Things like tuning the number of mappers reduces CPU memory. Doing so could yield great performance improvements without knowing much about the business logic of the job. So last but not least is at job level. So you can go and understand business logic of the job and try to simplify that by perhaps removing one unnecessary join or aggregation. Next, I'd like to talk about the S3 consistency model we had to work with for the next generation cluster. One big change for our new cluster is switching the primary storage from HDFS to S3. Those two storage systems provide different consistent model. HDFS is the file system that is strong consistent. Changes are immediately visible. On the contrary, S3 is the object storage service that is eventually consistent. There's no guarantee a change is immediately visible to the client. This might cause missing file issue without user even know it. Here is an example of read after write consistency for HDFS and S3. In this chart, from left to right is the timeline. From top to bottom are the writer clients, HDFS reader, and S3 reader. In this example, writer client set color to green to both HDFS and S3 at T1. For constant read, HDFS read client, at any given time after write complete, it always read the color as green. For an eventually consistent reader, S3 reader might return none at T2, then green at T3, then none again at T4. Eventually, they will always return the red color, green. What does this mean in Spark? Here's one example. A Spark job writes out 5 files in the same folder, but when another Spark job trying to read those files shortly after creation, S3 may only return 4 files instead of 5. In this case, the reader Spark job doesn't even know it missed one file. So the next question is, how often does this happen? In general, the chance of inconsistency of listing of S3 folder is super small. AWS S3 team had conducted a test, showed the chance of inconsistent happens less than 1 in 10 million times. We also conducted a S3 consistency test internally. The chance is even less than 1 out of 15 million. When we were designing our solution to this problem, there were a lot to consider and balance. Two most important ones are write consistency and read consistency. Write consistency is whether the job could write output consistently without missed, duplicated, or corrupted files. Read consistency is whether the job could read files in a folder, no more or less than it's supposed to read. And the consideration list also continues. As you can see here, there's a lot to consider. So we had compared a lot of different kinds of solutions, ranging from simple ones to really complex ones. I won't take too much time to cover each one of them. The quick takeaway is S3 is not an HDFS, and there are a lot to consider when you want to switch from HDFS to S3, especially how to deal with the consistent model change. You can use this table later as a reference to make your own decision when it comes to dealing with S3 consistency models. To solve this issue, we took a hybrid solution that combines 3 different tools. We use S3 committer to improve writer consistency. Daniel will cover the difference between different committers later in this talk. We also use number of file monitor to make sure mission-critical jobs won't miss any files when reading. In parallel to this, we widely use data quality frameworks to ensure the data holds high data quality standard. This helps us to prevent data issue introduced by all different kinds of reasons, including S3. This approach works well for our current jobs and doesn't require a ton of effort to implement. However, this approach needs workflow owners to be aware of this issue, and they need to adopt those tools in their workflows. For long term, we are looking into implementing a sophisticated solution to solve this problem systematically, such as Iceberg from Netflix and Data Lake from Databricks. With that, Daniel will talk about the difference between two of our primary storages, HDFS and S3.
Okay, thanks, Xin. Now let's compare the performance between HDFS and S3. In our test, HDFS and S3 achieve similar throughput. However, metadata operation is much slower on S3, especially for move. S3 move operation is essentially a copy and then delete. Unfortunately, we use a lot of move operations in Spark. This is especially obvious for applications with simple logic but produce a lot of output. For example, one of our Spark streaming application which persists Kafka stream to the storage. On HDFS, the microbatch runtime is 13 seconds, but on S3, it is increased to 55 seconds. Most of the time, the application is doing nothing but moving the files around. This caused the microbatch pile up. Let's take a closer look at what are those move operations. The first two move operations are common to every Spark application. That is, after task finish successfully, commit task will move file from task attempt folder to the task folder. Then, after job finish successfully, commit job will move it again to the job output folder. This is necessary because we don't want the result of a failed job or task be visible. In addition, some applications need more move operation. For example, in a dynamic partition table insertion, Spark will save the job output to a staging folder before move the output files to the Hive table location. This is because Spark need to figure out which partitions are newly added by the Spark job, so it can add the partition metadata accordingly. However, we cannot afford those more operations. We need to find some optimization. There are several existing solutions for the first two more operations. File output committer algorithm 2 skip the job level move operation. It moves output file from task attempt folder directly to the job output in commit task. So we don't need to move it again in commit job. This removes the job level move operation. The task level move operation is still there. However, compared to job level move operation, task level happen in parallel, so it is lesser a problem. Further, inside Pinterest, we already have a direct output committer used in MapReduce, which also removes the task level move operation. Direct output committer write the file to job output directly for every successful task attempt. However, the first two approaches suffer some degree of data correctness issue. For file output committer algorithm 2, if job fails and cleanup is not done properly, successful task output will leave there, so downstream job will read incomplete result. For direct output committer, if job fail and cleanup is not done properly, downstream job will read incomplete or even corrected output. A better solution is Netflix S3 committer, which uses S3 Multipart Upload API to upload files directly to job output location without leaving incomplete or corrupted output, even if the job fails. We also realize other more sophisticated solution, such as Netflix Iceberg, which is the successor of S3 committer. However, the focus of Iceberg is to provide the transactional support, which we don't really need in our use cases. And also S3A committer from recent Hadoop distribution. However, it is tightly integrated with S3 guard, which adding extra operational complexity. So we decided to adopt S3 committer, which solve our need, but still simple enough. S3 committer make use of AWS S3 Multipart Upload API. It consists of 3 stages. First, user need to initiate multipart upload to instantiate. Then, multiple upload part API, which actually upload the file to S3. Finally, a lightweight, complete multipart upload will tell AWS to weaving the pieces into a complete file and make it visible. If anything goes wrong, user will invoke abort multipart upload to remove the partial uploads. There are 2 operational tricks for multipart upload API work. First, unfinished part files are saved in a separate staging area of the S3 bucket until complete multipart upload or abort multipart upload is invoked. It is not uncommon Spark application die in the middle, so neither complete or abort multipart upload is invoked. User cannot see partial upload using the usual S3 command, but AWS will still charge you for the partial uploads. So it is important to set up a S3 lifecycle policy to remove partial uploads after a certain time. Second, abort multi-part uploads require a separate S3 permission. We need to explicitly grant the permission, which we often miss in practice. In the task, S3 committer will write the output to the local disk. After task succeed, inside commit task, S3 committer will invoke upload part API to upload the output from local disk to S3. However, the output is not visible yet. S3 committer will invoke complete multipart upload later in commit job after all tasks finish successfully. This two-phase commit-like approach will ensure there's no corrupted or incomplete file if the application fails. And in the meantime, we don't need to move any files. In addition, S3 committer also upload part files in parallel, so we can achieve better throughput than HDFS. Still, we have one more operation remaining for dynamic partition insertion. It is required because we need a way to track the new folders added by the Spark application and add partition metadata to Hive Metastore for those folders only. For example, the Spark application produce a new folder ds equal to 2020 January 12th in the staging directory. By listing the staging directory, Spark can figure out the new folder ds equals to 2020 January 12th and add partition metadata to Hive Metastore, along with moving the folder to the table location. To get rid of this move operation, we change S3 committer to write a table level tracking file to record the partition generated by Spark job. After job finish, we can read the tracking information. We can read the tracking file to find out the same information. However, if multiple Spark applications are writing to the table at the same time, there might be conflict on tracking file. We haven't found a general solution yet. Instead, we enable it in certain applications, which we know there's only one application writing to the table at any given time. With the removal of more operations and increased upload throughput, the micro-batch runtime decreased from 55 seconds to 11 seconds, which is even better than HDFS. By switching to S3, we also encounter some S3 specific issue. Rate limit 503 error is a common one. AWS support can partition the S3 bucket and prefix. They can even set up a cron job to partition a future prefix which doesn't exist yet. However, we don't feel this solution is reliable and implement our own task level and job level exponential backup logic in S3 committer. We also make the parallelism of part file upload tunable, so user can tune their job to maximize the throughput, and in the meantime, avoid exceed S3 limit. Here is a list of improvements we made on top of Netflix S3 committer. Besides rate limit and parallel part file uploads we just mentioned, we also add the e-tag check for multipart upload to make sure the integrity of the file. We fixed the thread pool leaking for long-running applications. We also removed the local output generated by the task as soon as upload part is finished, so we can save the local disk usage. The biggest benefit by switching to S3 is the cost saving. We reduced the cost by 80% compared to HDFS. In the meantime, S3 achieved better SLO. The claimed SLO for S3 is 4.9 for availability and 11.9 for durability. In comparison, our HDFS can only achieve 3.9 availability in our current support level, and the difference of durability is even higher. Besides storage, the new cluster is also different in resource scheduler. The old cluster is using Mesos, and the new cluster is using Yarn. There are a couple of things we miss in Mesos. First, we can manage every service inside Mesos, but in Yarn, long-running service such as Zookeeper, Hive Metastore are separate entities. Mesos plus the job submission system, Aurora, provides a lot of functionality. It can support simple workflow, long-running job, and clone job very well. It supports rolling restart, and it has built-in application health check. All of those are missing in Yarn, and we have to rely on external workflow systems, such as Pinball and Airflow, and sometimes the customized scripts to achieve those. There are a couple of things we like in Yarn. It provides global view of all running applications. It has better queue management for organization isolation. And more importantly, all our other clusters are already using Yarn. With better visibility and queue isolation, we can use the resource more aggressively with Yarn. The computer cluster costs less compared to Mesos. Before we end the talk, I have another 2 slides to show the current status of Spark adoption inside Pinterest. We are still in early stage. Among all load of Hadoop cluster, Spark represents 12% of total vCore usage. We have a few Spark streaming use cases, but mostly it is for batch processing. We are actively migrating our Hive workload to Spark SQL. In the meantime, we are looking at ways to migrate our cascading scaling job to Spark. We are adopting Dr. Elephant for Spark in our code review process. We integrate Dr. Elephant with our internal metric system and also include several features from Spark Lens. As a side effect, Dr. Elephant increased the load of Spark history server significantly, and we are in the process to improve the history server performance. If you have interests to work with us on any of those, please talk with us offline.